So I am going to start with some computation which appear often in the fluid mechanics. And this computation allows you to go from Lagrangian to Eulerian coordinate. Or vice versa. So let me state it as a theorem. Let V be from 0t cross RD into RD. And so what I am going to state on RD will be very valid of the torus because the function on the torus are just function on RD, which are periodic. Be a Lipschitz function. I don't need such strong assumption. And let S from 0t cross RD to RD be the unique flow defined by S dot of Tx is V of T, S of Tx, and S of 0x is x. Okay, so because the function is Lipschitz, this problem has a unique solution, and you can even get uniqueness on the weaker assumption than Lipschitz. So you are going to call, if you call S the position of the particle, describing the trajectory of the particle, S dot will be the velocity of the particle in Lagrangian coordinate, and V will be the velocity in Eulerian coordinate. Now define let mu be a probability measure on RD, and define sigma t to be the push forward of, so let me call it sigma 0, of sigma 0. So here, what it means is that the integral over RD of f of y sigma t dy is the integral over RD of f of S of Tx sigma 0 dx for every f which is continuous and bounded support. Then the derivative with respect to time of sigma plus the divergence of sigma v equal to 0 in the sense of distribution on 0, 1 cross RD. And the second statement, if there exists, if f is from, let me call it f bar, from 0t cross RD is set to RD is such that the acceleration Tx is f of Ts of Ts. Then, so I am saying if I have Newton law in Lagrangian coordinate, I can write Newton law in Eulerian coordinate by saying that dTv plus gradient of V equal to F bar. So this is my acceleration in Eulerian coordinate, and that is my acceleration in Lagrangian coordinate. So let me try to prove that. We are to show let phi be a function of class infinity of compact support on 0 t cross Rd. The question is to know if we have 0 is the integral from 0 to t dt, the integral over Rd of the derivative of phi at a ty plus gradient y of phi at a ty v of ty sigma t dy equal to 0. So this is the question. Saying that this whole in the sense of distribution mean I integrate by part formally, and the equation I get, I want to know if that equation is satisfied. But using the definition of push forward, this is the integral from 0 to t dt, the integral over Rd, the derivative of phi at a t s of tx plus gradient y phi of t s of tx inner product v t s of tx, the whole thing sigma naught dx. We want to see if that is 0. But now I am going to use that this is s dot. If that is s dot, then this whole thing is d over dt of phi of t s of t x. And I can change the order of the integral. So this integral will become the integral from 0 to t, the integral over Rd, and dt sigma naught dx. And that is the integral over Rd. I am going to write what is there. Phi of t s of tx minus phi of 0 s of 0x sigma naught ds. And this is 0 because phi is a compact support, and so phi of capital T is identically null, and phi of 0 is identically null. And so I get what I want. So we have the first part. The second part is Easy. So from that equation, call this star, differentiate star, to obtain s seconds of Tx equal to the derivative of V with respect to time at Tx plus the gradient of V at Ts, S dot. But this is the derivative of V with respect to time at Ts plus the gradient of V Ts. S dot is the V of Ts if I use a star. Call this 2 star. This together with 2 star this is 2 star. This together with 2 star tell me that this left-hand side equal to the right-hand side. But S will be 1-to-1, and I can conclude that F bar of T equal to dTV plus gradient of V, which is the desired result. So now let me go back to what I was doing last time. We have U star and F, which is defined on the torus cross the set of probability measure on the torus into R. And we have the following fact. Whose proof has been postponed. If T, so here we assume that it is of class 3. So if T is small enough, the following has a unique solution. dTs of T SQ equal to negative gradient Q of F S of T SQ S T S push forward mu. So given mu, a probability measure on the torus, so this is second derivative, and S Q is identically Q, and dTs of 0 S Q equal to gradient Q U star of S of 0 SQ S of 0 S, push forward mu. And this is for S T in 0T per Q on the torus. And so I said that this solution, if I change a mu, the solution will change. And so S is in fact a function of T, S, Q, mu, which I denoted by sigma ST. So this is a very standard notation if you are looking for a solution of a PDE, which at time S is the identity. And at time T satisfy a differential equation. I use this notation, which is very convenient when you want to state a semi-group property. But this depends on mu. And so I add the dependence on mu. And this is a function from the torus to the torus. And the theorem. Let T naught S be in 0T and mu be a probability measure on the torus. Then set sigma T naught, sigma T to be sigma S T mu push forward mu naught. So this is defined for every T in 0 T. Then the first statement was the semi-group property. If you take sigma from S to T naught at mu, and you compose that with sigma T naught. So I'm going to S from T naught to T, but sigma T naught. So at time T naught, the distribution of the system is sigma T naught. At time S, the distribution of the system was mu. So I take a system which at time S was mu. I let the system evolve. At time T naught, the distribution becomes sigma of T naught. So it is very natural that this will be ST of mu. And so if this did not depend on a mu, that is a classical semi-group property from differential equation. Now, if you compare this theorem, this is my force in Newton's law, then F bar will be negative gradient Q of F. And here my velocity V, I can write it as V of T y is S dot of T, S inverse of T y. So I can write it as Vt is S dot T, composition S T inverse. This is what I'm going to do here. Set V of ST mu to be the derivative with respect to time of S sigma St mu composition with St mu, where St mu is the inverse sigma St mu. Okay. So I am going from Lagrangian to Eulerian coordinate. Then the V satisfies also a semigroup property. Then V of St mu will be V of T naught T sigma T naught. So this is a consistency property. I have my unique flow evolving. At time S, when the distribution is a mu, my velocity is a v. And the system is evolving. At time T naught, the distribution becomes sigma T naught. And this is saying that the velocity is consistent. It is also useful to have that identity. The identity map is sigma S T naught of mu composition sigma T naught S of T naught sigma T naught. In overworld, the map in overworld, the inverse sigma S T naught mu, the inverse of that map is sigma T naught T of sigma T naught. And so if I understand well the property of sigma st for every st, then I have understood the property of the inverse of the sigma. So proof, we gave a proof of I last time. Now let me prove 3I before 2I. By I, sigma S T naught of mu, composition sigma T naught S of sigma T naught equal to sigma S of mu. But by definition, sigma SS is the identity. So by I, identity is sigma SS of mu, which is this expression, and that proves 2i. Now for the proof of 3i, of 2i, I am going to differentiate both sides of I. Differentiating both sides of I with respect to t. We obtain the derivative with respect to time of sigma st mu is the derivative with respect to time of sigma t naught t, sigma t naught, composition sigma s t naught mu. Hence, if I use the definition of the velocity, v st of mu is dt sigma t naught t, sigma t naught, composition sigma s t naught of mu, composition S T S T of mu. Now, I am going to, this is the identity map. So I am going to write that this is the derivative with respect to time, sigma t naught t, sigma t naught, composition sigma s t naught of mu. And then I am going to compose that with the identity map. But the identity map, so here I am using 2i. The identity map is sigma t naught s of sigma t naught, composition sigma s t naught of mu. So I have used the fact that this is the identity. Composition s t of mu. Now, this and that is going to give the identity. Okay, let me follow. So let me follow my note. So if I make this the identity, so call this one. And so I write that this is equal to dt sigma t naught t sigma t naught composition sigma s t naught mu composition s t naught of mu composition S T naught T sigma T naught. And then I am going to write that this is the identity map, and that is dt sigma T naught T sigma T naught composition S T naught T sigma T naught, and that is the T naught T sigma T naught. And so that proof so here I have used 3i. Okay, so reminder, recall that we define U of S Q mu equal to U star of Q sigma S T 0 mu push forward mu minus the integral from 0 to S V S L of mu applied to Q square plus F Q sigma ST SL mu push forward mu DL. And I want to show that this U is a solution to the master equation. So I can use the notation sigma t as before. This is sigma s t mu push forward mu. And if I do that, this will be sigma 0, and that will be sigma L. Minus the integral from 0 to S V S L mu of Q square over 2 minus F of Q sigma L plus dl, where sigma t equal to that for every t between 0 and capital T. So theorem. First, U of T, Q, sigma T, equal to U star of Q, sigma 0, minus the integral from 0 to T of V of S L Q square mu of Q square over 2 minus plus F of Q sigma L dl. Okay, and so here is the observation I would like to make. Here I have S, and there I have S. Here I have a T, but there I have a S. And so this is this is an improvement over that. So I am saying that if I change S here by T, I don't need to change it here. And we will see that this is a consequence of that identity. Second result. We have the derivative with respect to T of sigma plus the divergence of sigma V S T mu equal to 0 in the sense of distribution on 0 T cross the torus. And third, the gradient of U at a T Q sigma T equal to V S T mu. So you can recognize this from a regular Hamilton-Jacobi equation where what will play the role of the value function is related to the velocity. And as a consequence, you satisfy the master equation. Okay, so let us try to prove that theorem. proof by the definition of U, U of T Q sigma T equal to U star So make the following observation. Make the observation of this is sigma S of 0, mu, applied to mu. And so sorry, I want to make that observation here. This is sigma S0 of mu applied to mu. And so if I want to write, to prove the theorem, I would have to replace this by sigma T of 0, sigma T applied to sigma T. This is what I have to replace that by to be consistent. So by the definition of U, U of T Q sigma T is U of Q sigma T of 0 sigma T, push forward sigma T, minus the integral from 0 to T, V of T L sigma T of Q square over 2 plus F of Q sigma T of L sigma T applied to sigma T. dl. But sigma T of L. So I am going to do the computation for every L, and later I will take L equal to 0 and L arbitrary. Sigma T L of sigma T applied to sigma T. By definition, sigma T is sigma S T mu applied to mu. Now I am going from S to T, T to L. According to this theorem, that is giving me sigma S L of mu applied to mu, and this is sigma L. So that take care of this, and it take care of that. What remains is this. So call this 3, 4, 5. And if I compute V TL sigma T according to that, according to this is V S L of mu. So what I have done is I replace T by L and the T naught by T. So if you do that, then you see that you get this expression. So call this 3. Using 3, 4, and 5 with the definition of U, we obtain I. So now we have I. We will do what happens often in when you are dealing with a value function. By I, if I write U of T plus H, Q sigma T plus H, this will be U star of Q sigma 0, sigma 0, minus the integral from 0 to T plus H of this thing dl. So I am going to write it as U star of Q sigma 0 minus the integral from 0 to L minus the integral from L from 0 to T minus the integral from T to T plus H of the same expression. But that is U of T, Q, sigma T, minus the integral from T to T plus H of this thing, expression. Consequently, U of T plus H, Q, sigma T plus H minus U of T, Q, sigma T divided by H equal to 1 over H negative the integral from T to T plus H of what I integrate. And so letting epsilon, letting L go to 0, we obtain letting epsilon go to, letting H go to 0, we obtain 6, which is dTu of T, Q, sigma T, plus the Wasserstein gradient the velocity at time q, sigma t, equal to negative v of t sigma t q square over 2 plus f of q sigma t. Where v is a velocity is such that the partial derivative of sigma with respect to the divergence of sigma v equal to 0. So if I can show that vst is such a velocity, and if I can show 3i, then I have a master equation. So 2i recall that dt sigma st mu equal to v st mu composition sigma st mu, and sigma t equal to sigma st mu push forward mu. By today's exercise, we obtain 2i. Today's exercise said if you relate the velocity in Lagrangian coordinate to Eulerian coordinate, if you define this path as a push forward by the flow, then the flow satisfies, then the path satisfies the continuity equation. Now it remains to prove 3i. I want to differentiate this using the definition of u. We have gradient q of u s of q mu equal to gradient q of u star of q sigma 0 minus the integral from 0 to s gradient v st mu of q v st mu. It will be L plus gradient f q sigma L dl. So I am skipping some small thing. What is supposed to appear here is the transpose of the gradient of v, not v. But you need to check that the gradient of v is symmetric. So you need to check that the velocity is a potential, is a gradient of a function. And later I will come back, tomorrow I will come back to that. So once you check that, then what I wrote is correct. Now, if you remember the exercise we solved, the exercise said that when you have a Newton's law, we have dt t sigma equal to negative gradient QF. The exercise says that when you have a Newton law, then in Eulerian coordinate, it is dt v plus gradient v equal to negative gradient QF. Therefore, I can replace gradient v plus gradient QF. I can replace it by negative dt v st mu by the exercise. And so that is gradient Q, U star of Q, sigma 0. I replace it by, so this negative, I replace it by plus, so I have a plus. And if I use the fundamental theorem of calculus, it will be V S S mu minus V S 0 mu of Q. Now, let us go back to the definition of sigma. We have the gradient of, we have dt sigma st at time 0 mu is gradient q u star of sigma s0 of q sigma 0. This is how our initial condition was defined. Therefore, the velocity is this composition, the inverse of that. And so this is VSS mu of Q. So this proof, which I gave at S, I can give it for any small t. And so, in fact, I have the conclusion that, in fact, gradient Q, U of t, Q, sigma t, is VST mu of Q for every t between 0 and capital T. And that proves 3I. So corollary. U satisfies the master equation. So proof. Combine I and this. I am going to give a name to that. So call this 5A. No, 6. Combine 5 to I of the previous theorem. With 6 to obtain the corollary. So you see that if you replace, this is telling you that Vst is the velocity for sigma. But that is telling you that gradient Q of U is then a velocity of sigma. And so you replace V, the velocity, by gradient Q of U. And this is the non-local term in the master equation. So I will stop here.